This conference will now be recorded.
Hello and welcome everyone. My name is Kristoffer Martinsson and I work as Field Application Engineer at Know-How Solution. So in this webinar, I'm going to talk about debug and real-time trace of a multi-core system. This webinar is intended for people that at least have been using Lauterbox Trace32 for a little bit, so they are familiar with the tool. Before I get started, I'm going to just give you a short introduction to Know-How Solution. Know-How Solution, we are a distributor of software development tools, mainly for the embedded industry. We have different kinds of tools like compilers, debugger, but also testing tools, for example, unit testing, static code analysis, and also CAN and Bluetooth and USB products, etc. We have our main office in Malmö in Sweden, but we also have offices in Denmark and Finland. And these are just some of the tools or some of our suppliers that we have. And today I'm going to talk about tools from Lauterbach Development Tools that you see on the top left. I just want to mention the equipment that I'm going to use in the demo part of this presentation. So a standard setup when you need to debug your embedded system over JTAG is that you need a setup like you have here on the picture. It contains of two parts. It contains of the rectangular box called the power debug unit, and it also contains a debug cable. So the power debug module is a generic module that works on all architectures that Lauterbach supports. And there are two different versions of this. And I'm going to use a Power Debug Pro here today, but there is also more simple called Power Debug USB. The difference is that the Power Debug Pro has Ethernet connection on top of USB, and it can also be extended with a trace module. So the Power Debug module is a generic box, but the debug cable, it's not. That's it. The debug cable is specific for the architecture that you would like to debug. For example, an ARM core or a tri-core PowerPC or something else. And today, since I'm going to show some trace features as well later on in my demo, I also have a power trace module. This is intended for a scenario where you would like to do off-chip trace. And with trace, I mean recording exactly what is going on in the CPU. So the power trace module is a generic trace module that works on all architecture that Lauterbach support. And it's mainly a large memory. So it's a trace memory with up to 4 GB. And on top of the power trace module, you also need an architecture-specific preprocessor. It's because every trace interface for different suppliers or vendors could be different. So there are different preprocessors for ARM and for tri-core, etc. So these preprocessors could be for parallel trace interfaces, but nowadays also for serial trace interfaces and so on. So this is just a picture of what I have here on my desk that I'm going to use in my demo. So I have the Power Debug Pro module with the power trace and a debug cable here connected to the JTAG connector on my board, and I have a preprocessor for ARM here connected to the trace port on my board. The embedded system that I'm going to debug here today is contained of an SoC from Xilinx, so it's a Sync UltraScale. So it consists of a quad-core Cortex A53 and a dual-core Cortex R5. So that's the SoC I'm going to use for demo a little bit later on. And I'm going to do my demo on an ARM processor, but most of the things that I'm going to mention today is also valid for other architectures like tri-core, PowerPC, and so on. So there are two different scenarios that I would like to talk about here today. And the first one is SMP debugging, where SMP stands for symmetric multiprocessing. This is used when you are debugging several identical cores. And normally they share one single operating system, for example, Linux. So it's intended for when you have Linux that runs on all cores and the operating system distributes the application or different processes to the different cores during runtime. So that's the intention of when you would like to debug in SMP mode, so to say. And with SMP debugging, you only have one instance of Trace32 running to control all the cores. And you cannot control them individually. So when you hit the breakpoint in one core, all the cores will stop. And regarding breakpoints, when you set the breakpoint will be set on all cores. There are ways to make a special breakpoint that only stop on a specific core, and I will come to that in my demo. But for simplicity in my demo that I'm going to do, I'm not going to use an operating system here at all. And more, I will have like a bare metal on each single core here that I'm going to debug, but that's not the normal use case. Normally, you in a system like this, you have an operating system like Linux, VxWorks, or some other operating system that support SMP. Oh, sorry. So I'm going to switch to Trace32. So I'm going to go through some of the specifics that you should be aware of when debugging an SMP system here. And it's both on setting up, configuring the debugger, but also on how you use the tool during debugging when you like to do different things. So I've already executed my script, and as you know, if you have been using Trace32, everything can be done with commands and scripts. So I have run my script to set up the board, but I have it open here to show a few things that are specific when you are debugging SMP. So in my case, I have selected the CPU that I would like to debug here. So I've selected Sync UltraScale APU. When I did this, the debugger knows that this is a quad-core Cortex-A53. And after that, I've been using the command core assign to select the cores that I would like to debug. Here, you can choose to only debug some of the cores in the CPU, but in this case, I've selected to debug them all, and that's actually the default setting, so I didn't have to execute this command here. But for ARM cores, or if you have a brand new ARM CPU, it might be that Lauterbach has not implemented full support for it yet, so there is no CPU selection specific for this SoC. Then you could still debug that by using the example like I have here. So this is the alternative way to do it, is all that's commented out here, like selecting the CPU core, Cortex-A53, then most likely some JTAG settings like these here, and then specifying the number of cores. So 4 cores. And then most likely you need to add a few more settings here. But this is specific for ARM. For most other architecture, you can't do this. So the important thing when it comes to setting up SMP debugging is the core assign. And how do you see in the debugger that you are debugging 4 cores in this case? You see it down here at the bottom. there is a 0 here, and if I right click here, we see the number of cores here. So there's 0, 1, 2, 3. And notice the difference here. Here we start at 0, but for the core assign, we start the core numbering at 1. So if you would instead debug only 2 cores, I'm going to do that. So I'm switching to the command line, and I disconnect the debugger, and then I run the command core assign like this. Then now I select only to debug core 1 and 2 like this, and then mode attach like that. Now, if you look down here, we see that we are only debugging core 0 and 1, so only 2 cores. So that's the core assign that select which cores that you would like to debug. I'm going to switch back to debugging all 4 cores like this. Okay, so if we open some windows here, like list source and also register like this. The content of these windows always displays from the perspective of the core that's selected right now. And you see it, now it's core 0, and I can switch by right clicking down here to core 1. And as you can see, these windows are changing. Now we see it from the perspective of core 1, core 2, and back to core 0. So it's controlled by this selection here. And if you want to have this selection also in another window, there is something called target system state. I'm running this command here. Here you also see the cores that you are debugging. Let's make this one smaller like that. And actually here you can just double click on a specific core here, and it's the same as right clicking down here. The command from the command line to do the same thing is core.select, and just specifying the core that you would like to debug. For example, core select 3. And now we have changed to core 3. So let's switch back to core 0. But if you have some window that you always want to have it to display from a specific core, you can do that. So there is an option to many of the windows that's available in Trace32, or many of the commands, that is /core. So for example, the list command here, I can edit this command and choose core 1 like that. And I can do the same for the register window. And then I can open another one for core 2 like this. So now we have, let's make this one smaller. So now we have one window, one list window showing core 1 and one for core 2. And so it doesn't matter which core that's selected, this window will always show the same content. One important thing is when it comes to single stepping, that you should be aware of. When you're debugging and would like to single step your code, if you single step in assembler mode, that I am right here, or mixed mode, so with single step, single instruction, you only single step one core. So if I, in this view, only pressing this button, I'm only single stepping core 1. But if I instead do here, I only single step core 2. If you use the global buttons up here, single stepping in this mode, you will single step the core that is active or selected down here. So in this case, core 0. So now we're single stepping core 0. This is only true for assembler mode. If you do it in high level mode and you single step, all cores will execute when you single step, because that's implemented as a with breakpoints more or less. So then all cores are started. Okay, so let's close some of these windows here. And I will just open window like that and break. So what about breakpoints? As I mentioned earlier, if you set the breakpoint, I'm going to do this from the command line with the command break.set on the function called sieve. The default when you set the breakpoint in SMP mode is that it will stop no matter what core that hits the breakpoint. So it could be any of the 4 cores that execute the sieve function, and execution will be stopped. So we will see it by pushing the go button. And as you can see here, we did stop, and we can see here it's core 3 that did hit the breakpoint. If I start execution again, now it was core 2, etc. And there we did stop in core 3 again, and so on. If you have a breakpoint and you would like to specify it should only stop when the breakpoint is hit on a specific core, you can do that by editing this breakpoint and use the advanced field. So down here at condition, you could use a function called core, like this, for example, core 1. So it should only stop when core 1 hits this breakpoint. You see the condition here, and if we start execution, it will take a little while. There it did stop, and as you can see, it's core 1 that did hit the breakpoint. But you should be aware of when you're using anything down here is that this breakpoint is intrusive. So it's actually because what is possible to implement in the CPU is the thing that is on top here. So in this case, the execution will be stopped every time any core try or go into the sieve function. But then the debugger, when it detects that the CPU has stopped, it will evaluate the expression down here and check if it's core 1 in this case. So it is intrusive, and this could be detected by this yellow lines here on this red bar here. So that indicates that the breakpoint is intrusive. If I would just remove this like this, now you see it's a solid red bar here. And as I mentioned, when it comes to the cores, they all stop when you hit the breakpoint. And that you can see here, they all are in the stopped state. So every time you hit the breakpoint, all the core stops. And how is that done in the CPU? Yeah, this depends on the architecture that you are debugging, which type of core, but there's normally some kind of cross-triggering mechanism inside of the CPU that is used. So the cores will more or less stop, maybe not exactly on the same clock cycle, but yeah, but at least just a few clock cycles. So this is just the debugger just program the CPU to use this cross-trigger mechanism. So let's remove the breakpoints here. Okay, so that was some of the specific parts when it comes to debugging a multi-core system or an SMP system. I just want to show you a few things when it comes to tracing as well. So let's open a trace window like this. When we trace an SMP system, we normally trace all the cores in the SMP system. So in this case that I have here, I will trace all 4 cores at the same time. And this is true for most ARM CPU, but for some other architectures like Tri-Core, there it's not possible to trace all the core at the same time. This is a limitation of the CPU. So for TriCore, you need to select a few cores to trace because you can't trace them all. There are, for example, some triple core devices, but you can only trace 2 cores. But for ARM, you trace them all when it comes to SMP. So let's make a small trace recording here for a few seconds, like that. And what is specific then for trace when it comes to SMP? Yeah, as I mentioned, we trace all cores and we can see the core number here. So in this normal trace list window, the trace data will just show in the order it comes out of the trace port, or how it is written into the trace buffer. So here is core 1, and as you can see, here is something coming from core 3, and if you scroll in this window, you will see core 2 again, etc. So there is trace data from all the cores in the system. So for example, if you would use the find button and you would like to search for the entries to a specific function, I'm using the sieve function as an example here again, and use find all, you will find all the entries of this function in all the cores. So here we can see that the sieve function is executed on both core 1, 2, and 3, and we can see all the executions of this function here in this window. If you would like to see only core from a specific core in this window, you could again change this trace list command like we did with before. We can use, for example, core 2. Then this window will only show content from core 2, and if you will use this find function again like this, it will only show the executions of the sieve function in core 2. So here were the only 3, so there are 1, 2, 3 in this window from core 2 in the other window. So as you can see here, the slash core option was added automatically on the trace find when I did hit the find button on in this window where core 2 was to the header there. So, and the same is of course true for chart window. If you have a chart window with core 2, then it will only show the trace chart from core 2. If I go down to the command line and use symbol like this, it would show the chart for all cores. As you can see here is core 0 here, and if I scroll down, you will see core 1, 2, and 3, etc. So if I run this command again and add like a core 1 here. So in this case, if you have 2 windows like this showing trace chart for 2 different cores and you would like to synchronize them to see what is going on in the other CPU when you're executing something. For example, if you want to see what's going on in core 1 when we're executing something in core 2, you can add the track option to these windows like that. Let's add it to the other one as well. This means that if you click somewhere, you get a blue line also in the other window showing what. So if I go to, for example, if I would like to know what is going on in the other core when we enter the sieve function, I just click there and we can zoom in here in the other window. We can see that it seems to executing, in the func3, func13 function here. So the track option can be used to synchronize different windows. And this is actually not only for multi-core debugging, this can be used for synchronizing different windows always in the debugger when it comes to trace. There was one more thing that I would like to show that's a little bit specific for SMP debugging, and that is if you would like to use trace for profiling. There are a lot of profilings command in the perf. Perf stands for performance. For example, function runtime, task runtime, etc. So some of the commands are available here, but I'm going to do this from the command line. So I'm going to use the trace command .statistics.symbol. When I open this window, let's make this one a little bit bigger, we will see the execution time, or how much time we spend in different function. And again, the default for this view is that we separate the core. So here we see core 0, and these are the top function when it comes to execution here in this core. And as you can see, it's almost add up to 100%. So if you will add everything together or sum everything for core 0, it will sum up to 100%. And if I scroll down, you will see that core 1, it will add up to 100%, etc. So here you have a separation, so you get the numbering for each specific core, and each core has 100%, so to say. But here it is actually, it could be useful to use the command or the option for this trace statistic symbol to merge all the cores together, or merge the statistics from all cores together. So there is a merge core option like this. You will see here it will look a little bit different. Let's sort this one again like that. So now the statistic is not for separate cores, it's merged together. So now the total is 100% for all 4 cores in this case. And for example, func13 is the top. It has been executed 42% of the time. If you look in the other window here, you will see func13 here, 38% on core 1 and 59% on core 2 and 70% on core 3. But in this case, it's added together and then divided by 4 in this case, since we have 4 cores, and that will sum up, add up to 42%. So there are more options here when it comes to this, but it's good to know that merge core is a good one to use when you like to do profiling. Okay, so that was all I wanted to show when it comes to SNP debugging. So I now will switch back to my slides. And by the way, I didn't mention it in the beginning. If you have any question, type them in the chat, so we will have them answer them at the end. So next is AMP debugging. So asymmetric multiprocessing. So for debugging, we use AMP debugging when we're debugging several cores that are different types. Or actually, you can debug in AMP mode also when the cores are of identical types. The difference is for SNP debugging is that each core that you debug has its own instance of trace32. So you have the possibility to control each core separately. So you can halt only one core and let the other cores be running and so on. And the normal use case is that when you do this is that each core in the system has its own operating system or its bare metal. So it doesn't have a shared operating system like Linux. And so this gives you a lot more flexibility because, as I said, you can control each core individually, and you can also set breakpoints on individual cores. And of course, it's possible to also have a combination of SNP and AMP. So for example, in my picture here, I have an example of the system with 8 cores, and there's a Linux SNP system on core 1 and 2, and there's another Linux SNP system on 3, 4, 5, and 6, and then there are 2 cores, 7 and 8, that run bare metal. So in this case, you would have 4 instances of trace32. The first instance will control core 1 and 2. The second instance will control 3, 4, 5, and 6, and then you have 2 instances for core 7 and 8. So you can select how you like to set it up. So how you would set it up depends on how your system is configured. But the important thing with AMP debugging is that the cores doesn't have to be identical. So actually, in my case, as I mentioned in the beginning here, I have Cortex A53 cores and Cortex R5 in my SoC. But actually, you don't even have to be all ARM cores. It could be tri-core and the Cortex M, for example. That I know that some tri-core devices actually have a Cortex M inside as well, also. Or there could be some ARM cores with a DSP. So that's what's normally what AMP debugging is used. So how does it look, and what do you need to consider in the debugger? Okay, so I'm going to open up a script here to configure an AMP session, or like that. So this is, I've just taking out some of the important parts when it comes to AMP debugging. And actually the first part here will just set up the Cortex A53, and I've already configured it since that's what I was using with SMP. So I can skip this part of the script and I'm going to run down here. So the important thing when it comes to SMP debugging is that the different instances of the debugger need to be able to communicate. And that is done by the intercom system in Trace32. And as you can see here, there is an intercom command with intercom.name. And what this will do is that you will only give this instance a specific name. And I've called it A53, since this is controlling the Cortex A53s in the debugger. And when we run this command, as you can see up here at the header of this window, it's added here. So now we see that this is the debugger for the Cortex A53. And if I go down here, this one will start a new instance of Trace32, this command, and we will call it, give it a name, R5. So this you can call whatever you want. And it is of the type ARM. That's the architecture that we would like to debug. So let's run that command. And as you can see, now we have two instances of Trace32. I'm going to arrange these windows next to each other. Okay, and then the intercom command is used to send commands or do on the other instance. So here we have the intercom command and R5. This means that we should run this script, do ultra or RPU slave, blah, 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 on the R5 instance of Trace32. So let's do that. And as you can see, something happened in the background. So the debugger now for the R5 is configured. So now we have two instances. So here we have the Cortex A53, and we can control it, and we can single step it, and so on. And we can do the same thing here in the Cortex R5 debugger. You can start execution, halt execution. So at this point, we control the different cores individually. Or actually, in the Cortex A53, we're actually controlling all the 4 cores there, and on the other instance, we only control one Cortex R5. But normally, you would like to have a synchronization in between the different instances. So when one hits a breakpoint, you would like the other one to also stop. And I did have this configured here, or the configuration for this here in the script. So I'm going to also open the sync command here. Let's make this one smaller. And so to configure this synchronization between the different instances, you use the sync command. So here we have, for example, intercom all sync connect others. This means that the intercom and all means that this command should be executed on all instances of Trace32. And you would run the command sync connect others. So it will just connect the different instances of Trace32 together. So let's run that. And as you can see, this is populated here in this. So here we see which instances of Trace32 that's connected together. So in my case, I only have 2 instances of Trace32, but here you can have a list with many if you have that. You should be aware of this intercom is done by UDP communication. So you use a UDP port, and the default is port 10,000 for the first instance, and then the second one with 10,001. This can be modified and to some specific port if port 10,000 is used by you for something else. And then now these are just connected together, but we need to configure them for synchronizing go and break. So this is what comes here: sync master break, sync master go, slave break, slave go, etc. So I will just run these 4, and these actually correspond to these different checkboxes here. So I believe that this is the default settings that most have when it comes to multi-core debugging. This means when I push the go button, all cores will start, and if I push break or hit the breakpoint, all the cores will stop. So I can, for example, set the breakpoint here in the function speed trouble, and like that. And I can set another breakpoint in the other core in another function, like that. So now I have 2 different breakpoints set, and if I start execution, there, this Cortex R5 did hit the breakpoint in the function leaf of Julia, and it says stopped at breakpoint down here at the bottom, and the other core, it says stopped by external debug request. So this is the cross-triggering mechanism that I talked to you earlier about that has caused the other core to stop. And if I hit go again, now the Cortex A53 did hit the breakpoint in speed trouble, and this Cortex R5 stopped by external debug request. But sometimes you have a system that you are debugging several cores, and one core you would like to have running all the time. So, for example, if I remove this breakpoint, so in my case, I could, for example, make sure that the Cortex R5 is never halted. Or if it hits its own breakpoint, of course, it should be halted, but it shouldn't stop when you hit the breakpoint in some of the other cores. Then you can uncheck this slave break. Slave means that if there comes a signal that the other core has stopped, it shouldn't react on it. That's what slave means. So if I uncheck that, this core should never stop. So I start, and as you can see here, we hit the breakpoint in the Cortex A53, but the Cortex R5 is still running, and I can run again on the Cortex A53, and the Cortex R5 never stops. So it will only stop if it hits a breakpoint in the Cortex R5. So, and if you have more than 2 cores, this could be very complicated. Then you might also need master break. Master break means that when this core hits a breakpoint, it will send a stop command more or less to the other cores. And if the other cores have configured slave break, then they will also stop. But that's how you see it. So that was master and slave means in this case. So let's halt this manually and delete the breakpoints there. Okay, so what about trace when it comes to AMP? Yeah, when you have AMP debugging and trace, you can actually control which core that you would like to trace. So I'm going to open, let's close some windows here. So, but the default, or not the default, but right as it is configured right now in my system, is that I will trace all the cores. So if I start the execution and record a few things in trace and look at it, as you can see, we actually have trace here for both cores. But we can, oh, sorry, we should have actually this one enabled now. With the, when we are in AMP debugging, we can actually choose to turn trace off for a specific core. You will see how this then look. It looks like it's recording here also here, but this is because the trace buffer is shared between all the cores. If we stop the execution, actually there is nothing useful here in the trace here for this core. So we have disabled trace for this core. But you can trace them all at the same time if you want to. Also, I mentioned earlier the sync command. So let's make a small recording here again and look at the chart window like that. If you would like to synchronize in between the trace buffers in the different cores, you can do this here as well. I mentioned earlier the track option like that. And let's do it here. And if I click here, actually nothing happens here. There is one configuration that I have not done yet to be able to synchronize this track in between different instances of Trace32. And if I open this, this is done by this command. It's called sync extract. So if I run that command, and now I click here again, as you can see, you see the blue line in the other instance is moving also when you click here. So you can see what is going on in all the different CPU at a specific time. So that's what's all I wanted to show in this webinar. And so now it's time for some questions. And I see there already are some questions here. And the first question is like this. How complicated is Trace32 debugging for Linux kernel and /user space? I would say it's a little bit more complicated than a bare metal or a more simple RTOS. But if you have configured Trace32 correctly, it's possible to debug both kernel and user space at the same time. And actually, we do have some videos on this on our YouTube channel. So if you just go into search for Know-How Solution on YouTube, you will find our channel. There are two different videos, one for setting up debugging of the kernel and one other video for setting up debugging of user space. But if you have configured debugging for user space debugging, you can also debug the kernel, so to say. So I will recommend you to look in there if you were interested in that. And the next question is, do you need some special debug connector on your target PCB for tracing debugging, or can you do it with the standard JTAG pins? Yeah, today I have showed you some things that you can do with just JTAG, and some are for tracing. So you can debug and set breakpoints, single step your code looking at variable with just JTAG, and then you could debug as many core as you like. But if you would like to do tracing, I mean record what is executing inside of the CPU, there are two different ways to do it. Either you do it with an on-chip trace buffer inside of the CPU. Then you can do it with a standard debugger, so only a JTAG connector on the board. But the trace buffer then is very, very small. So it's kilobytes in size. So then you normally can just record what's going on for a millisecond or something like that. But if you want to do off-chip tracing, you need to have a specific dedicated trace port on your PCB. There are different versions on it depending on the architecture that you would like to debug, but there are parallel trace ports that could be up to 16 signals, but there are also serial variants of it where there only are 2 signals that you need in the trace port. So it depends on the SoC that you would like to debug. So that was all the questions I have here in the chat. So if you have any more questions, please type them in. Okay, there seems like there are no more questions. So, but if you are interested and would like to have more information or know more, please contact us at Know-How Solution. You have already our emails and so on, so you can just answer one of the emails that we got for the invites and so on. So thank you very much for joining, and yeah, and we'll end this webinar. Bye everyone.